Here is the common-emitter configuration again. We want to look at its low frequency response. This means that we are to find the expression for FL. This will help us determine which factors influence FL and how we can manipulate them to achieve our desired value. Now let's go through the steps which will help us determine the frequency response. The first step is that you have to open or short all the DC sources. In our diagram, we have to short VCC and VEE and open I. Secondly, you have to replace the BJT with a small signal model of your choice, and you have to ignore C-pi and C-mu. For simplicity's sake, we are going to be neglecting R0 and Rx. Now, once you're done with these steps, we are to consider one capacitance at a time. So, for a chosen capacitance, short the other two capacitances and Vsig, then find the total resistance across its terminals. The cutoff frequency omega for that particular capacitance would be 1 over Cr, where C is its capacitance and R is the resistance across its terminals. Simple, right? So let's do it for all three capacitances. Here we are for CC1. CC2 and CE are both shorted, and so is Vsig. All we have to do is find the resistance across the terminals of CC1. This comes out to be Rb parallel with Rpi plus Rsig. Correct? Now why have we added Rb parallel with Rpi with Rsig? Remember that Rsig and the parallel combination of Rb and Rpi are not in parallel. Why? Because the capacitor CC1 is between them, so they don't share two common terminals. And since we are only looking at total resistance across the capacitance's terminals, so we have to add them together. Now let's do the same for CE. Notice that we are performing the small signal analysis directly on the circuit. This is a good practice and saves a lot of time. Now for CE, you can see that the capacitance is in series with the emitter terminal. So we are going to be employing the T model. What we can do is that we can reflect the base resistance network into the emitter side. Let me show you how. Instead of multiplying Re with beta plus 1, we divided Rb parallel with Rsig with beta plus 1. Obviously, if we had reflected the emitter onto the base, we would have gotten equivalent results. Moving on to CC2, this is the simplest. All you have to do is add Rc and Rl. Again, Rc and Rl are not in parallel because CC2 prevents them from having two common terminals. So we write omega 3 equals 1 over CC2 multiplied by Rc plus Rl. So how does this exactly help us finding an expression for FL? Comparing the three expressions, we can see that omega 2 is the largest. This is because the resistance that CE faces is quite small. So small that even if we use a large value for CE, omega 2 is usually the highest of the three break frequencies. This is the case when F1, F2 and F3 are distinct from each other. By distinct, I mean that they have considerable difference between their values. In this case, the larger F2 is going to influence FL more, and we usually take the value of FL to be F2. However, what happens when F1, F2 and F3 are not distinct? In this case, FL is simply taken to be the sum of F1, F2 and F3. And so, we find a good approximate for FL, and combining it with our expression for FH, we can design the bandwidth of our amplifier as desired.